Well, I think we can get started, y'all. The recording's on. We have folks in the room. Doors
All right,
closed. I
let's
think
go.
we're all set. So, yeah, go ahead and get started.
Yeah, so hello. Welcome to the HDF session adhesive meeting. I apologize for not being there with you. That wasn't my intention when I submitted the proposal for this session, but here we are. I really wish to thank ESIP first for allowing me to have this fully remote session. And it's really very generous of them. And I also want to thank the staff, Alicia and Jail, I think, who are helping me, who are the ground support for this session. And today, I also want to apologize because the plan in the agenda was to have another session, which we didn't get the permission to present today after initial approval. So so far it's Mark and me, and so we'll have time for questions, for discussions if people want. Yeah, so let's begin. So I'll hand over to Mark. So Mark, I think, is also in another conference, if I'm not mistaken. So luckily that conference is on the East Coast. So we have some room here to adjust and accommodate. And he can tell us a little bit more about him. And I think he has a very interesting presentation. And I think you are all at this session because of his slides. All right, Mark, please take away.
Okay, thank you, Alexander. Normally, Alexander and I are usually in the same state, Virginia. As he mentioned, I'm actually coming to you from Pittsburgh, where I've been partially organizing JuliaCon for the Julia programming language. So I originally presented a version of this talk to the HDF group, and I've tried to adapt it for ESIP. Although I was just told that maybe you have a more bias or interest in ZAR. So I'll consider that as I kind of move along here. I'm coming from a little bit different background, as you might imagine from my title slide here. I've been trained as a biological scientist, mainly in systems and cellular biology. Although I've come to the Geneva Research Campus to mainly focus on imaging applications in biomedical research. And there I'm employed by the Howard Hughes Medical Institute, where perhaps we have the fortune of being a private foundation and not having any restrictions on what we can talk about. So I'll try to talk to you a little bit about some file formats, about HDF5, ZAR, and perhaps a bit of TIFF, or GeoTIFF, as maybe you may call it. So let's get going. Okay, so my favorite cartoon here that I keep thinking about, and ever since I really got into imaging and data, has been thinking about this XKCD cartoon. It starts with the situation. There are 14 competing standards. They all don't quite work. They don't quite meet our needs for some reason, and we end up creating yet another 15 standard. And I think on one hand, we create standards because we need to. There's something that's painful that's about the prior standards. But sometimes I don't think we learn the lessons of some existing standards. And so something I really wanted to do before I went head on into something new was also try to compare prior standards and other formats and see if we could maybe find commonalities between them. And kind of the ultimate manifestation of this was trying to see if we maybe could even combine file formats or put our data in such a way that is accessible via more than one format. A big motivation for me in this application is to avoid data duplication. My institute does a lot of imaging. A few years ago, a lab at my institute won a Nobel Prize for super resolution microscopy. And at this point, we are producing hundreds of terabytes per week, and that rate is growing. And so we really do have a situation where we need to carefully think about how we format our data. And the other part of this is I can't afford to have multiple copies of this data. So we can't have one format in TIFF and another format in HDF5 and another in ZAR. This would completely defeat any kind of attempts to compress the data. Another thing that I think about is just accessibility to software. Some software may have been written many years ago before some of these newer standards existed. And so something I really wanted to do was make sure that we could use both older standards and also the newer standards, which maybe have advantages such as being more directly cloud optimized. But I think one question I have here is what does that cloud optimization bring us, and could we make older standards also cloud optimized? I have to say that my supervisors actually don't quite like what I'm doing here. They would much prefer I focus on APIs. But I think this brings up a whole nother problem. The API solution is definitely a solution for software developers, but not typically users. For software developers, we can pick our APIs, but users are not ones that could do that. And this also brings to light something else that we had invented at my institute a while ago, was something called N5, which actually stands for not HDF5. And a version of this was eventually a prototype for what became ZAR. In many ways, I think the ZAR leadership right now is a combination of two communities, of one from bioimaging and brain connectomics, which is very much something my institute is very interested in, and also the geosciences, the earth sciences. And so I find it very fitting that I have the opportunity to communicate with you today. Okay, so that aside, I think it's also been pointing out to me that there is a blog post by, I think, Element 84, who I understand is one of your sponsors. And it asks, is SAR the new COG, Cloud Optimized GeoTIFF? And I found this really interesting because I started coming to this conclusion as well, that there's some commonalities between these two formats, but also perhaps HDF5. And so I'll get into the TIFF, the COG part a little bit later, and we're going to focus a little bit on maybe a little background ZAR and HDF5. In the HDF5 version of this talk, I was a little bit more critical on the HDF5 side, but maybe this time I'll critique the ZAR side. And basically kind of what I really kind of want to consider is, are these things really different? What if these things are actually all pretty similar? What does that mean for how we're allocating our limited resources? And could we maybe take advantage of these similarities? So I'm going to give a little primer about SAR, particularly SAR version 3, because I'm going to be exploiting a new feature in SAR version 3 called sharding. And I'm going to compare SAR v3 shards to HDF5 because there's some reminiscent qualities in both. And then explore the possibility that these things actually could be the same thing. They could be the same file, in fact. And lastly, we'll bring TIFF back in and kind of dovetail with the Element 84 blog post that I referred to just now and see if these all could be one thing. So perhaps I don't need to tell you too much about this. What is ZAR? ZAR is kind of intended to be something simple for n-dimensional arrays stored in some kind of hierarchical fashion. Depending on who you ask, my bosses usually explained it that perhaps HDF5 is doing too much work and it would be much simpler to just exploit the file system or perhaps object value store. And this is in some ways cloud optimized in that we don't have to go searching through a bunch of metadata in order to figure out where our data is. In SAR version 3, which I participated in the writing of the specification, especially the sharding codec, most of the I would say file metadata or format metadata is stored in a SAR.json file instead of a .c array or .c group or other dot files. Chunks are normally stored as individual keys, as in SAR version 2, although they're arranged in a slightly different manner. In SAR version 3, the default chunk key encoding starts with a C. We have a lot of chunks in there, so we don't confuse it with other potential structures. Although I think this was a bit of a superficial change from SAR version 2, causing a bit of pain for some clients that only know how to read SAR 2. And the basic idea is that we put each individual chunk in each individual file, and the pain point that usually drives my systems admins, especially my file system admin, a bit crazy is that this ends up creating millions of files. Trying to move one of these is extremely difficult, and for this reason, we created something called the sharding spec. The idea behind the sharding spec was that we would take multiple of these individual chunks. This could be really small, 32 by 32 cubed. I don't know if that's small to you, but that starts to work for us. But we can assemble these chunks into larger shards, and then multiple of those shards could then comprise a larger array. And kind of the thing that defines a chunk is that the chunks are individually compressible and decompressible. Now, you ask me, I think this starts to sound like HDF5, although, and maybe from, depending on your API, you might think of this as netCDF. While HDF5 and netCDF are typically in single files, they can be arranged as multiple files as well. And so they could be completely analogous to a shard and be assembled into a virtual data set. I'll get into that a little bit later, but I wanted to get into the sharding spec. So we put multiple of these chunks inside the shard, but we need some way to figure out where the individual chunks are within the shard. And for this, we needed some kind of index. And the SAR authors, SAR specification writers, ended up choosing to go with 64-bit unsigned integers to identify the byte offset and the number of bytes or size of the chunk. I think this is perhaps one of my contributions to this codec is that I insisted in calling this n bytes instead of size just to disambiguate if we meant bytes or bits or whatnot. So I hope maybe you appreciate that this is more clearly the number of bytes. And another contribution that I made here, and while we were discussing this, was the need for a checksum. I have a CRC32 there, and 32C, which is a particular polynomial that's used for this. And part of why I kind of insisted on this checksum is also part of my experience with the HDF spec and needing to protect integrity of metadata. I believe another contributing factor was the involvement in NVIDIA in comparing them to their APIs, which were saving their own proprietary data format. But eventually we all agreed that having a 4-byte checksum would be useful. The original intent for this was for this to be a part of the same file as a shard, and this could go either at the very end or very beginning. And for cloud-based shards, this chunk index could be retrieved via something called a byte range request, which is supported in cloud storage such as Amazon S3, but increasingly emulated by many other vendors of storage solutions. At my institute, we use VAST Storage, which has a compatible S3-like API that allows us to request parts of files. From the beginning, you could just calculate, get the 0th byte all the way up to the nth byte that you would know about from reading the star.json file. From the end, the original thought there was we could use a negative byte range request, a single negative number, which referred to the number of bytes offset from the end of the file. However, I think in subsequent actual implementation of this, we found that not many services actually supported negative byte requests, and it became more common to just implement explicit byte range requests with a starting and ending byte. If anything, I think this is one thing that I would have changed about SAR version 3 sharding, in that this is very un-SAR-like, in that it combines metadata and data in a single file. This is often a critique for that I have towards my HDF group friends here, because this is something that is often done and I think does make things a little bit more difficult when trying to find your data. I would have personally preferred that this chunk index actually be in a separate file, perhaps adding a .index, and maybe be more reminiscent of the approach of Kerchunk. I believe there's other approaches that have been mentioned, such as virtual reality SAR, but I won't discuss that today. But nonetheless, there's this structure here that indicates where the chunks are within the file. HDF5 has a very similar structure called a fixed array data block, which exists in version 3 of the HDF5 specification, particularly for filtered dataset chunks. This is quite similar in that for each chunk, there's address and chunk size, analogous to the offset and n bytes of the SAR sharding spec, and there's an additional filter mask, something which SAR currently lacks. The chunk size and address are variable. They could be configured by the HDF5 superblock, but they could be 32 or 64-bit. And I believe the filter mask is typically set at 32 bits. The checksum doesn't use CRC32C. It uses something called Bob Jenkins lookup 3. But you can see that the basic overall structure is similar, although these are not exactly aligned. A more complicated version of maybe what I could talk about today is how to align them, but that's slightly out of scope. So could we format an HDF5 file or netcdf file as a SAR version 3 shard? There are a few possibilities here. One, option A, which I think is maybe perhaps the least hacky version of this, would be to take advantage of an HDF5 feature called the user block. The user block allows for user data to exist at the beginning of the file. And so that perfectly matches our application for the SAR v3 shard to be at the beginning. And at some fixed offsets, which can be grown exponentially, then we can follow that with the HDF5 superblock and the rest of the HDF5 metadata. To cloud optimize this, we could use settings such as declaring a large metadata block via the HDF5C library in order to consolidate the HDF5 metadata into a single block of metadata. This allows us to not mix metadata and data as much as possible. Another option would be to start the file with an HDF5 metadata, have the chunks go afterwards, and then at the very end of the file, make sure that there's still no metadata there, but that we add another data set, and this data set would serve as a SAR version 3 shard. If we could align the HDF5 FADB, the fixed array data block, and the SAR version 3 shard, while also addressing the matter of the checksum, we could actually perhaps relocate that part of the HDF5 metadata and have it double as a SAR version 3 shard index. I'm not going to go too much into that. That was more of a topic for my discussion with the HDF group, but you could ask me about that later if you'd like. So conceptually, the sharding concept is similar to a concept that HDF5 had introduced, I believe, last decade in 2014. I believe this RFC is from. Part of the critique here from the HDF5 side is that I think the best documentation for this is still the RFC and not from the actual implementation of this. And they differ slightly, but it's documented well enough at the end of the day. But similarly to the concept, virtual data sets allow you to take multiple files, take data sets from those files and combine them into one big data set, which is very analogous to SAR and especially SAR version 3 with sharding. And so there's a one-to-one mapping between those two concepts. And so essentially what we could do is we have shards be individual HDF5 files containing data sets, and then we could have basically equivalent to sort of that JSON HDF5 file, which basically assembles those shards into an HDF5 virtual data set. And potentially here, we could basically use the same chunks as both HDF5 chunks and SAR chunks. And so this is basically what that would look like. We would have a bunch of shards with this kind of file format, and you would maybe have even the star.hdf5, the star.json, that maybe would slightly duplicate some of the metadata, particularly the format metadata, by assembling these multiple files into this combined n-dimensional array. But basically, you could see that now we have this solution where we have taken advantage of overlapping concepts between virtual data sets and started resharding in order to reuse the data via either format, allowing you to use either API. Okay, so basically, the HDF5 would refer to each of those as components of virtual data set. SAR would basically use its chunk indexing and chunk key encoding to basically refer to those as individual chunks and their inner chunks. And so we have a way of combining SAR and HDF5. So how about now let's reintroduce TIFF, or especially cloud optimized GeoTIFF. And so I think the GeoTIFF part, the way I usually think about it from my perspective as a biologist, is that you guys had the insight of adding tile depth, allowing us to have 3D tiles. But maybe this makes more better conceptual sense as blocks or more generally chunks for n-dimensional data sets. And so perhaps we could go even further with the dimensionality there. TIFF, I think the TIFF specification requires a magic byte sequence to occur right at the beginning of the file. So the TIFF metadata is going to have to start at the very beginning. And I think if we go into cloud optimized GeoTIFF, basically you'll see that they use this technique of also trying to consolidate the metadata, the IFDs, all together at the beginning of the file in order to refer to image tiles later on. As I mentioned earlier, when combining HDF5 and SAR, there's this concept of the user block. In this case, if we're going to try to combine all three, what I'd like to do is use the user block for the TIFF metadata. And that's because we can store the SAR metadata at the end of the file. And so now we can basically create this sandwich of TIFF, HDF5, the actual data, in my case is usually image data, and SAR metadata. And these could now basically give you all three formats all at once. And that would allow you to open individual SAR shards as either HDF5 files or perhaps even TIFF files. So the way my application for this is that I typically need to do this very near to acquisition. I have microscopists who are trying to acquire data and they want to look at what they're acquiring. So in order to do that and make this simple for them, and they typically may have very custom implementations of microscopes where they're using some programming environments such as LabVIEW to instrument their device. They may have very simple, a need for very simple implementations. And so one way I found to simplify that is just use a template-based approach. Either I provide a template for them and they fill in their data at the given location, preferably with chunking, but it could be tiles coming or planes coming off a CMOS camera. And alternatively, they could just write to an empty file, just skip a few kilobytes, leaving some room for the TIFF to HDF5 metadata, and then add their chunks. They don't need to worry about adding space in the end because that's easily done after acquisition. But nonetheless, we could then fill in the templated metadata, and we get a combined file, which allows us to simply have a file that can now serve as a TIFF HDF5 file or be plugged into a larger directory structure as part of a SAR array. So this is just a very short demonstration of what this can look like. I called this repository simple image formats because I was trying to take each format and simplify them so that we could basically play Legos with them as I've been trying to assemble these into the sandwich. But the demonstration here is basically showing that I can take what is essentially the same file and use either H5Py, libtiff, or Google's TensorStore as SAR client in order to read the exact same array data from the same file using those libraries. I could maybe then go and use H5Py to modify one of those files, that file in particular, make sure that it's put in the correct place within a SAR layout. And then we could basically go back and use those three libraries again and see we could open all the same data in all three. This takes advantage of the fact that I'm using uncompressed chunks here. And the reason for doing that is mainly because the layout of the chunks doesn't change in the file. The chunks are exactly where they are after the data changed. With compression, this might not be true. And in that case, you would have to manually update the HDF5, TIFF, and perhaps SAR metadata structures. In this case, I'm directly manipulating the files. I've explicitly built this sandwich of data between HDF5, TIFF, and ZAR. But one thought is that we could build systems to virtualize this. Instead of having these files actually exist on disk, we just add the appropriate metadata blocks as needed for whatever format the client is actually requesting. I think we could go into some of this. I think maybe I'll just skip in this. If we want to go through this, we can maybe do that in a Q&A since I'm getting close to time. With HDF Group, I just want to mention I helped implement H5 chunk iter, which is maybe a very efficient way of getting the location and of chunks and within the file, with an HDF5 file, which allows you to kind of rewrite that information for ZAR or TIFF. And here's some technical details. I'll skip that and just go to some closing thoughts. I think introducing a new format can be costly. We usually have good reasons for doing so. We're trying to do things that maybe those other formats didn't do or we didn't know they could do previously. But I think after some thought and thinking about what is the fundamental reason for, say, cloud optimization, I think it's possible to make both TIFF, as in case of cloud optimized GeoTIFFs, or HDF5 cloud optimized. My thought for multi-formatting is that we could save resources. And particularly, I think, from my perspective, this is usually in terms of developer time. But also perhaps software pipelines and whatnot. And I imagine that many of you may have also have regulatory processes to think about. Part of what allowed me to combine these formats today is actually that same cloud optimization process, which consolidates metadata. With consolidated metadata into discrete blocks, this makes it much easier to assemble them in a Lego-like fashion in order to create kind of these data sandwiches. And the final thought I want to get across here is that in many ways, GeoTIFF, HDF5, and SAR, they're all doing very similar things. They are, in this case, just trying to address the location of tiled or chunked data in our files. And perhaps we should take advantage of those commonalities. So thank you. I'm willing to take any questions if we're still on time, Alexander.
Yeah, thanks, Mark. Yes, any questions for Mark? Please go ahead and ask. I'll just mention that I really appreciate Mark doing Python examples because I think he likes Julia very much. So thanks, Mark, for using that other programming language for these examples.
My pleasure. I program in a bit of Java, Julia, Python, whatever it takes, and a little bit of C when I'm working with the HDF group.
Well, I have the microphone here in the room. Does anyone have any questions? Just raise your hand. I can carry it over. Comments? And if you're online virtually, feel free to add anything into the chat as well. Okay, there's an online question.
Okay.
I'll let you all read it.
Okay, let me see. I have to find the chat button again.
Oh, sorry. Is there a Git repo available?
Yes, I will post it in the conference Slack. Would that be the best place for it? So the Git repo mainly contains demonstration I did right at the end, the Jupyter Notebook. But basically, and something I've struggled with is trying to figure out what would be the best way to disseminate this technology. And some people have told me maybe making a library would be useful. I usually think about this in terms of templating. But yeah, I'd be really interested in where I should take this from here. More of what I'm more interested in is just kind of sounding out the idea and seeing who might be interested in this. And um, the more I talk about this, the more I seem to find some justification that people still want to use TIFFs for some reason in existing pipelines. The session notes, would that be on the, I'm sorry, which platform is that? I joined a bunch
You
too.
can email me if you want, Mark,
Okay,
afterwards
I
or
will do
something.
that.
I'll drop it on.
Yeah, and feel free to add it into the chat too, and then we can get it copied over as well.
Okay, I will
Yep.
do that.
Yep,
Okay, thank you.
yep. Are there any
So
other?
I have one
Sorry,
question
go
for
ahead.
Mark.
Sure.
So these HDF5 files that will be like ZAR shards, how many HDF5 datasets with data do you think should be in that one single HDF5 file? One HDF5, or that's the equivalent of netcdf variable, just for those in the Is that how you're thinking about it?
So I would think it. So I would refer maybe initially to some of the use cases in the virtual dataset RFC. Um, so usually for individual files, the maximum size I like to deal with is about 2 GB. And at 2 GB is the limit because that's the number of bytes you can address with 31 bits. And I think we still have a few systems out there, particularly in the web, that may be using signed 32-bit integers to address bytes in the file. And so going beyond 2 GB is usually where I find a pain point. So basically, if I'm doing sharding, the largest shards I will typically produce is just under 2 GB. Whereas for chunking, I usually like to keep them small so I can address small units of those. And something I didn't really talk about, and something that differs between the different shard implementations is the order of those chunks in a shard. Some people like to put them in lexicographical order. Other people like to use perhaps a Morton curve, basically a space filling curve that allows you to aggregate and read nearby chunks in a single read. But typically, I like smaller chunks so we can get to smaller bits of data without loading more than you need while keeping shards at about 2 GB.
All right, thanks.
Yeah, thank you, Oksana.
And nice that you mentioned that Element 84 blog about ZAR and Cloud Optimist GeoDiff, because I learned about that blog after I found that you presented your this talk, and so I said, hey, I know a guy who has 3 formats into the same place, not only 2, so we can go one more better than the Element 84 folks.
Right.
And
I think
so
I did try to reply to like a Blue Sky post on that, and so I'm hoping we can start a conversation there. With
yeah,
3 is too much, but
yeah.
the point is just that these things could work together.
Yeah, but that's what won you the spot on this session. I know the guy with 3.
Yes.
So yeah, all right. Well, thanks, Mark, a lot. So
Yeah,
do we
thank
owe
you.
someone some URL, or I'll drop it into the session notes in that Google Doc if you email me. But You can drop them in the chat if you want for people who are now online, however you want.
We have a question here in the room too.
Oh,
Hold on just
sorry.
1 second.
Sorry. No,
Nope, you're
absolutely.
good.
Thank you. I guess just the main question was, is there some sort of compromise? I mean, like, this sounds great to have, multiple files or multiple formats all on a single file, but is there some sort of compromise to the formats, performance, or anything that you've come across?
You're muted, Mark.
Hello?
Yeah.
Yep.
I got it. Yeah, I'm muted.
Mark was
That's
muted.
talking. So
Yeah.
hopefully you can hear me.
Yeah.
So I think there's several questions there. So the way ZAR was originally explained to me was that, it's much better to have the chunks broken up into individual files and not put together in some big file like HDF5. And yet this sharding thing seems to go against that narrative. And so I think the initial question there would be, does sharding somehow compromise performance or simplicity or implementation? And it does add maybe an extra complexity to the call. You have to get the chunk index from a shard. And so that does add something, and you have to think a little bit about how many chunks you have and how big that chunk index might be. I think, when in the specification, there is some thought that maybe we would all agree on a particular order, and maybe if the chunks were all the same size, we could easily compress this index. But I think in the end, we just ended up going for the most generic version we could think about that didn't require contiguous chunks and whatnot. But that definitely is another layer there. And part of my critique that I made there was that you actually have to go find the byte range for this now, and you have to calculate that, and that adds some complexity to implementations. Whereas I think the more SAR-like thing would have been to add the index in its own key in a key value store, which could be a file system. And so I think if there's an opportunity for me to kind of change that, that's something I would be going after next. For multi-formatting, I think this makes much more sense in a read-only situation where the chunks aren't moving. Because the second the chunks move, now we have to update the maps in the other formats. And if I can't, say, align HDF5 FADB, a fixed array data block, with the SAR index, then that definitely adds complexity. And as far as I know, the TIFF tile offsets, I don't think can be combined easily with either of those. And so you have a situation where you need to keep the metadata in sync if you're writing back to these. So the way I would typically think about that is if you start writing back to this, that you should maybe rename it so it's more clear that you're working with it as a particular file format, and maybe only think about multi-formatting it again as you export it or share it back into the cloud in a read-only sense. But I think that those are two main drawbacks. Compression definitely adds some complications also for writing.
Thank you. One follow-on then is, you have them all three in the file. Is there not, have you explored a way where the other two could be derived from one? Is there flexibility enough in one state? Because some of this is kind of overlapping, as you point out, very similar, and that it could just be a tooling thing where you kind of emulate it instead.
Yes, absolutely. So my personal preference at the moment is to use the HDF5 API to do manipulations, just because I find that to be the most mature of the APIs. Although, depending on how you want to work, perhaps you have processes that can easily work in various parallel ways on individual chunks. In that case, maybe ZAR might be better. But in either case, the situation would involve writing the chunks, extracting locations of those chunks, and figuring out how to input that data into the other formats. HDF5 makes it easy to read that a chunk of metadata, but not particularly write it. And so you might have to manipulate HDF5 at the byte level. And so that's why I think I typically think of manipulating these files at the HDF5 level. Something about the SAR API is there's usually not, well, there's multiple SAR APIs, right? Multiple implementations. And most of them don't really let you think about files or shards as individual files. Whereas that's usually the way I conceptualize and parallelize things is that I usually have one thread working on an individual shard, just so that threads don't have to communicate. But you have more advanced multi-threading, multi-processing processes, such as MPI, and you can coordinate that, then maybe you could do something else in terms of how you distribute your data.
Thanks so much. Does anyone else in the room have a comment or a question before I? Okay. Are there any more online questions? Okay, we're good. All right, well, a big hand of applause. Thank you so much for your presentation.
Yeah, thank you.
And I'll hand it back over to you, Alexander.
Yes. Thanks, Mark, very much. I think that this probably won us the most technical session of the EC meeting, if there is such an award. No Jupyter Hub lights over here. Just the stuff that makes the science work. And so thank you very much. I will you now, because it's dinner time on East Coast. I think you deserved your dinner with your Julia friends. Just don't tell them that you use Python here on this presentation. It's all good. And so thanks very much. I'll take over from here. I'll talk about something else. Although obviously, let me just fire up the my presentation. Let me see how it goes. All right. Okay, hopefully you shall very quickly see my slides. So what I wanted to talk about and what was the title of this session was HDF5 2.0. And I chose this provocative title, Cloud Optimized, from the start, mostly because I think that and the HDF5 2.0 is the next release of the HDF5 library that is currently on track sometime in September this year. And so we're talking about 2 months from now. And I chose this title because I think that this is going to be the first release where working with HDF5 files in a cloud object store, in this case S3 specifically, is going to be somehow like a thoughtful experience. That's, there are some little enhancements here and there in the last couple of releases, but this one is trying to make all these things and some more into a bit more better user experience. Again, for this release, the good news will be only for cloud optimized HDF5 files. Nothing for the current typical HDF5 files, but I think we can do something even for those in the future releases. I only learned at this EC meeting, I knew about the work of preparations, but I didn't know that was actually happened. But I learned that the ISA-2 satellite and its product ATL03, I think, is now actually cloud optimized HDF5 files. So they're starting to appear in the as operationally produced data. I also think, as far as I know, that the NICER satellite, which is about to be launched, I think next week or very soon, will come out again completely with HDF5, cloud optimized HDF5 files. So hopefully with this release and those files appearing now, people's experience will be much better. And again, as I say, people's experience, it's again goal that make HDF5 files and the library as a good citizen of this new multi-format, multi-API multi-programming languages universe related to science and cloud computing. So, honorable mentions, what I'm going to talk about is result of contributions from people like Mark and other people from open source community, and also 2 projects that are that funded some of the work. And so what's in HDF5 library 2.0? So some of the things, there are many others, but I try to tailor these things to the ECIP community, obviously. So from 2.0, the library versioning will follow semantic semantic versioning convention. You may be surprised, but so far that has not been the case. Some changes about CMake building the library for those who do dare to build the library from source. There will be some new data types. There are some default settings that the library will now have to optimize the user experience working with cloud optimized files. We have a new backend library for the read-only S3 driver, which is the driver used to access the HDF5 files in S3. And I'm talking about some HDF5 filter thinking and my wishes. And by the way, now that I mentioned this, I just want to say that Mark is the newly appointed maintainer of the HDF5 filter plugin for Z standard compression. So if you like Z standard compression and it's not working for you well in HDF5, Mark is now the guy you're going to be talking to. Anyway, sorry, Mark, but I just now realized the connection as well.
I've also been working on the C standard for ZAR as well. So
there you go. There you go. So what do we mean with the semantic versioning? So, so far the library, HDF5 library releases always had 1 dot something something. And so that one first number was meaningless, essentially, for all practical purposes. So that's going to change now. So from 2.0, the major, minor, and patch numbers will mean something. And of course, it's easy for me to say now because we haven't yet made the 2.0 release, and maybe the life will force some changes here. But so far, the thinking is that the major version really changes whenever is the file format changed. So there are several versions when it comes to HDF5 library, but file format, the HDF5 file format also has its own version. And changes sometimes, again, into how data are stored force the change in the file format. For example, I think what Mark was mentioning about the checksum changes, supporting different checksums in the HDF5 fixed array data block. That would, for example, be a reason to change the file format version. So those kind of changes, or any kind of a change that introduces application binary interface, would force major version change. What is ABI compatibility? Well, that's basically, in the most simplistic terms, this is what forces you to recompile your application with the new version of the HDF5 library. If you want to upgrade to some other version of the library, or the latest version of the library. In the cases where ABI compatibility is preserved, you can just drop that version of the library compiled, and it's going to work with your code. Minor version, it's easy. Any change that doesn't qualify as a major version change. And so right now, thinking about maybe improved performance or new API, anything that, again, doesn't break those previous conditions for the major version upgrade. And the patch version is really currently thought to be, don't think, just upgrade, don't worry about it. Nothing surprising or new here that really you have to think about. Again, as I said, this is the current thinking. If the life is going to force some changes, we'll see. Because there's always some user of HDF5 somewhere who is going to find some problem with the way how he's implementing HDF5. So the CMake build system, I don't know how much of you compile and build your applications, but so far HDF5 libraries supported 2 major build systems, and one was newer CMake and the one was older Auto Tools. it was a huge drain on the company's resources to maintain both with the equal functionality or very similar functionalities. And so the decisions were made to drop auto tools and just support this newer CMake. And one benefit of switching to CMake is this one of the features CMake has, we call presets, which can really simplify how people store configurations for their builds and how they share them. And I actually wrote a blog very recently about that, actually how to build a library on top of H5 Pi in a Conda virtual environment. And there's the link down there about that. And it shows exactly how I use this CMake preset to build it on my laptop. Since this change is happening, one of the potential issues, for example, is all the other package repositories that are packaging HDF5 library. Are they going to be able to adopt or switch from AutoTools to CMake? One that I'm particularly thinking of in the context of VC community is Conda Forge. And so the next steps for us is to reach out to them and make sure that we help them sort of adopt CMake and try to work out from all the issues they may encounter, because they know the Conda build environment better than us, and we know CMake better than them. So we'll try to make the world a better place. So coming back to new features, after many years of lacking true support for complex numbers, HDF5 library will now have a brand new data type for native support of complex numbers. That's one of the reasons why you have 2.0, because this change introduces what I mentioned, ABI incompatibility. And so that's why this was the first of the features that really said, oh, we need to have a new major release of the library, and then we decided to switch to semantic versioning in the same go. So we missed NISAR, who has a lot of complex numbers, at least in some of the products. But because of that, we try to make the library a bit more intelligent, how to grandfather all the ways how people used to and currently store complex numbers in HDF5. And so if the library is used in a way that you specify for your in-memory data type these new native complex numbers. However, in the HDF5 file that you're accessing, these complex numbers are stored in these older grandfathered ways. The library will automatically recognize and do the right thing and convert, so that we kind of make it easier for people to actually get to the actual native complex data type to work with. And here I'm providing this kind of description of what is considered grandfathered complex number data type. So anything that has the same floating point data type for the sum as a compound data type in HDF5, which is like a structure. So there is a structure with two fields. These two fields have the same floating point data type and have names of these fields that resemble something like real and imaginary. So if the library recognizes any of those things, the library will say, oh, okay, this is a complex number, grandfather data type, and it'll do the conversion on read. How that's going to work in the wild, we shall see. But we use the one GitHub repository which documented quite a few data products out there that are storing complex numbers in HDF5, and we try to sort of follow that historical record. Talking about data types, there are going to be some data types really specific to AML data. They are defined in this open compute, can't see, well, let me see, open compute project microscaling specification. That's the consortium of the big guns in the AML world, NVIDIA's, Microsoft's, OpenAI, and all Meta and all that stuff. And so they got together and defined new versions of floating point values, specifically 8-bit and 6-bit floating point values. And so the library will bring those data types now and have support for them. Also, we'll also support this Google Brains 16-bit floating point value. Compiler support is all over the place right now. And so what that means is that without compiler support, really, there won't be good performance when working with these data types. But for people who are willing to wait a little bit more in terms of performance, you at least be able to save storage in HDF5 files because you'll store your floating point value in 1 byte. And so as the compiler support improves, then obviously we'll be able to roll out more and more of these things. But we decided to go sooner rather than later because we had some funding that could support this work. Okay. So where am I? Okay. All right. New changes. One of the things that I recognized when I interacted with a lot of people in ECIP community and regarding HDF5 files in the cloud was that the library's default settings were really not friendly to cloud optimized HDF5 files. And 2 of them were really highlighted as really, really critically valuable. And so the library in this new release will increase the data chunk cache size by default from 1 MB set wherever it was done, chunking in HDF5 to 8 MB. And frankly, I think chunking was so old feature in HDF5 that we probably talked about computers with 32 megabytes or 1 gigabyte memory. So today moving to 8 megabytes is nothing as far as the increase or the memory usage. So that will be now available. What also this helps is to all the software and all the users who are who uses, or at least somewhere in the software stack, they're actually using HDF5 library, but because of their software in between, they are not really able to configure HDF5 library anymore. So this should help them have better performance just by default. The other setting was file page cache, which will from 0 now go to 64 megabytes. This page buffer or file page cache actually is critical to really improve performance for cloud optimized HDF5. And so that, without knowing or ever thinking about it, you should now see much, much better performance when accessing file. This is what we can do on the HDF5 library side. Related again to cloud optimized or cloud computing, the library uses this ROS3 driver, as we call it, but what it means, it's read-only S3 driver. It's sort of the low level inside the library component that communicates with, in this case, S3 compatible object stores. Until this new release, the library had its own custom code for S3 communication written basically using curl library. We now switched to the Amazon's C S3 library written in C. And what it gave us out of the box is a complete support and advanced support with all AWS configuration and credential files, all the AWS environment variables, the tokens, the sessions, all that stuff. And also it has very intelligent way of handling communication with S3. It monitors itself, supports internal multi-threading, so all these kind of things. So we plan to expand our usage of its advanced features in the future, but as I said, it gave us this processing of all these environmental variables that we wanted, and also intelligent handling on non-fatal but failed S3 requests. It saved a lot of code for us to actually do the same thing. Also, because of this library now support naturally using S3 URI when you're referring to HDF5 files in S3. If someone used it before, you had to use the HTTP link URL instead of the S3 URI. And now we are also, again, naturally supporting S3. What was before available in the library, but maybe I thought would be useful to mention right now, is the fact that on file open, this driver, ROS3 driver, now caches first 16 megabytes of the file and keeps it forever until the file is closed. And that can help a lot, again, with performance of files if their content is kind of simpler or less complicated. So a lot of useful information fits into this first 16 megabytes. And also we fixed the bug that we discovered that essentially because of miscalculating the size of this cache for 1 byte, the library was making an additional S3 request for this cached first 16 megabytes. So that's eliminated now too. So at least one less S3 request must be good. With this new backend, we also allowed easier logging of ROS3 communication. In the current releases and so far, if you wanted to actually produce ROS3 logs and see what the library is doing and how many requests it's making and where it's going around the file to do its business, you had to build the library and actually change the code to enable this debugging. Now we are introducing a bunch of environment variables that you can set, and you're going to get this output on standard error or into a file. And the way how we did it is that one environment variable prints probably the most useful logging information for many users. And then if someone really wants to dive into the inner working of the Amazon's S3 library, then we have environment variable for that only too. But that's, you know, too much information almost for everyone. So what does it mean? So for example, if you have, I hope this is not too small for you, but if you set this, for example, HDF5 ROS3 VFD debug environment variable on, and then you put it on the same command line with the H5 dump, and you go after some file. In this case, this is a cloud optimized JEDI level 2A file that I'm using, and you redirect the actual H5 dump output to a dev null, so you don't want to see it. You just want to see the output of the debugger. Then you basically start seeing this output here, and it tells you, for example, about how he understood the URL, where it's going to go for, what's the key, what's the bucket. And then it starts showing you the requests. So you can see here, it first makes the head request to find out about file size and if it exists. We also introduced the user agent now that says, hey, I am the HDF5 library, my version. By the way, this is ROS3 driver doing the work, and I'm using the Amazon C S3 library. So someone who is doing the logs, now the library can be recognized for its work. And now you have this request like this get byte. You see this one from 0 to 16 megabytes. That's that caching request that gets that first 16 megabytes of the file. And then for the purpose of this H5 dump command, it needed only another request somewhere in the file for 8 megabytes, which is 1 page size, 5 page size, and that's it. So we basically had 1 head and 2 get requests, and H5 dump command can do its business. In case of this other environment variable, when you want to really get the Amazon C library, S3 libraries work, then you set it to info or trace or whatever level you want, and then the output goes into a special file. You can choose the file where you want this to output go, but this is kind of the output you will get. So, some people like to look into the log files. So this is for those aficionados. But again, for the problem, it can help obviously learn if there is something else. some issues here. So as I mentioned at the beginning about HDF5 filters, this is the last topic I want to mention. One of the things that came out with this cloud optimized HDF5 file thinking and discussion and is that we really should increase the size of dataset chunks, but also we should find more advanced ways to compress them, also to get on speed and maybe reduce their size or increase compression ratio somehow. And so in the world of HDF5, that type of software that operates on block of bytes representing one chunk, they are called HDF5 filter. And if someone writes a plugin between that software and HDF5 library, then that plugin is referred to as HDF5 filter plugin. And that's, again, when Mark was talking, he's now the maintainer of the filter plugin for Z standard compression library. And so these filter plugins come with their identifiers that are part of H5 dump, for example, output. You can see them. That's like their unique identifier. And anyone can create filter plugins. Some selection of the most popular ones, again, it's a subjective selection, are kept into HDF Group's GitHub repo, which is called HDF5 plugins. And so far, that repository was used really for HDF Group's internal needs to constantly test them against the library. Every basically push to HDF5 repository was triggering these tests. And also to produce HDF Group's own binary packages, including these filters. However, again, not many people, or at least many more people, get HDF5 library from other package repositories, don't go to HDF Group's place to download them. So I'm looking for ways to now reach out to these package repositories and their maintainers and try to tell them that they should really start thinking of including these plugins and this capability in their packages to make it really, really super easy and available to everyone. So we have a list of official plugins with a lot of useful information. And again, most filters are for data compression, although not all of them. So what is new in this world? We are updating this official document about registered plugins. We have documenting, for example, there is essentially a custom LZ4 compressed chunk format. It's, for those who are maybe familiar for LZ4, it's neither LZ4 block nor LZ4 frame format. It's a sort of a mix of something special and LZ4 block. So we are compressing, we're documenting that exactly. And why is this important? Well, it's important exactly for the reasons of now having different APIs. We have virtualizar, we have Kerchunk, we have what have you, now reading HDF5 files without OpenDep, also Hyrix server. They're all reading without HDF5 library. So this kind of information, the low level information, really is critically vital for that other software. Because effectively you have HDF5 file format description, fine, but any compressed chunk is essentially an opaque data format within HDF5 file format. And so this is really important to document. We are also really detailing the each plugin's configuration parameters, what they mean, what they represent. So again, to enable translation without any errors when it comes to supporting ZAR and other software. We also fixed a bug for LZ filter plugin in LZ filter plugin if someone is using LZ4, the later versions. And also what the 2.0 library will support is this newer open source library for deflate compression filter, or someone known it as gzip, or someone know it as zlib. So this zlib-ng library is about twice as fast as the standard zlib library that is traditionally used by the HDF5 library for deflate compression. And because of its widespread availability, a lot of data, pretty much, massive amount of HDF5 data out there is compressed with this deflate filter. So that's another thing that I'll try to promote to all these package maintainers, to really build a library with this zlibng functionality, because it can get packaged inside the HDF5 library anyway. So you don't need the external dependency on zlibng. So I think that's one, again, effort to make compression faster, improve performance. This is really my wish. I would like that we, again, move forward into this more advanced compression or other chunk filtering capabilities. For historical reasons, the two compressions that were available in HDF5 library since whenever are deflate and szip. Szip was plagued with certain legal licensing issues, so it was never really widely deployed, maybe outside of NASA EOS, this program. But it's not, also, I don't think it's used as much as deflate, but I may be wrong. However, as we know, now we have other compressions. And so I would like to see how I can organize communities or package maintainers to really think about building HDF5 library with these other filter plugins readily available. And currently what's available in HDF5 plugins, which means that it's daily tested with whatever version of HDF5 library code. We have LZ4, we have LZF, BZIP2, BLOSK, BLOSK2, Z standard, bit shuffle, bit groom, granular bit round, JPEG, and ZFP. Bit groom and granular bit round are not compression. They are different type. They're changing things. I don't want to. They're changing the values, making it better, or not allowing better, more efficient compression ratios. But again, as I said, I would like to make these things really, really more easily available, primarily to data producers and then obviously to data users to really change things. And I think this is the last slide. Yes, it is. So I'm done. And any questions?
Does anyone?
Thank you.
Okay, we have a question here in the audience. I'm going to take the microphone over.
No, so thanks. That was great. Oh, sorry. Okay, so that was great. Thanks, Alex. Anyways, so yeah, I was wondering if I write C++ code using the HDF5 2.0 library, and I open up a file or open up something using the S3 protocol, is it going to pull, so when it pulls out the 16 megabytes of information at the top, if I make subsequent calls, just interrogating the remote entity, the object, for like chunk offsets and sizes, is it going to pull that meta information out of the 16 megabytes that have already been extracted, or is it going to make repetitive calls to S3, or do you know?
Most generic answer is you don't know, depends where it's in the file.
Right.
It highly influenced the way how people create that content. So for example, my theory would be that, for example, if you're using NetCDF4 API, because of the way NetCDF, I think, done back in the past, that you first have to declare everything and then start writing,
Right.
adding data. And and again, as far as I know, they still retain that model. So it's safer to assume that all that information we're talking about will go into those first 16 megabytes.
Yeah, so what I'm thinking about is generating Kerchunk and DMR++ documents for things that are already in S3 without pulling the entire granule out of S3, but still doing it efficiently.
Generating. Yes, it should be more efficient. Again, there were some products. I had some experience with ISET too. There were some products who, either because of the content in those products, were smaller, less groups, less chunk, whatever, less HDF5 data set. They just happened to, all that information was in those first in 16 megabytes, and just essentially cloud optimizing was not really in any other way needed because you had everything in those first in 16
Right.
megabytes.
Okay, thanks.
But for others, again, that have thousands of HDF5 data sets in them, that's not probably going to apply.
Right. Okay, thanks.
You're welcome.
Thanks. Are there any more questions from the audience? Jill, do we have any online? Okay. I'm walking to the front of the room. Anyone has any last thoughts? Going once, going twice.
Yeah. And if anyone has any, as I say, problems or issues, or wants to carp about the HDF5 library or whatever, it's your opportunity now. The fact that I'm going to take a snapshot of the camera, just remember who that was. Don't worry about it. Nothing.
Well, thanks so much, Alexander. I know it can be difficult to present entirely virtual, so we really appreciate you and Mike being here. So let's give Alexander a hand. Thank you so much.
Thank you. All right, then. If that's all, then again, there was another talk, but we could not present it, and so this is all we have.
It was great. Thanks so much. And we
Thank you.
recorded this for, I know some people showed up a little bit later, but we'll have this recorded and we'll be sharing it back with everyone. So,
All right. Thank
yep.
you.
Yep. Thanks so much.
Thanks.
Yep.
Take care.